Sometimes you need ones and zeros. Lucky Wicks.
Then I end up getting nu dash is equal to nu 1 minus g capital H upon C squared. So this is the new frequency of the light photon.
I'm sure I got a new one. I got a new one. You're gonna start around here somewhere. I mean, you're kind of looking at things. You went from nothing, and your money piled up, and you actually graphed stuff out in their values, moving stuff around, saying, wow, you know, I mean,
a ball is affected by gravity. So as the photon is moving upwards against the gravitational pull of Earth, it loses energy, which is reflected not as a decrease in velocity, but as a decrease in its frequency. Now, in this calculation, I have assumed acceleration due to gravity to be a constant because I'm taking very small distances. If I want to sort of extend this argument and imagine a case in which the photon escapes the gravitational potential of a heavenly object. So a photon escapes the gravitational potential of a planet or a star. Then what is going to be the final frequency of a photon when it completely escapes the gravitational potential of, let's suppose, a star?
If you like a different game, but I have
also. So here I have a star, alright, so the star has a mass of m and radius of r. And there's a light photon which is emitted at the surface of the star, and this light photon travels away from the star and completely escapes the gravitational potential of the star. Then what is going to be the change in the frequency of that light photon? Can we calculate that? We can do that. It's quite simple actually. So let's suppose that when the light photon is actually emitted at the surface of the star, the light photon has an energy E and the frequency of nu, let's suppose. So what is going to be the potential energy at this particular surface? The potential energy of any kind of an object having mass m at this particular point is nothing but minus
-273
small m upon r. Alright, so m is the capital mass of the star, g is the gravitational constant, capital R is the distance between the center and that small mass m, and the small mass m is at the surface capital R, where the small mass is nothing but the mass of the photon.
Anything you can put down to those kinds of chains and rails.
If the photon completely escapes the gravitational pull of that particular star at infinite distance,
max
so let's
calculations.
suppose at infinite distance,
Got 400K
the
space
photon
movie.
has an energy E dash is equal to h nu dash, and its potential is basically 0. So I define that at infinite distance, it escapes the gravitational potential, so the potential is 0, but at the surface the potential is this much. So now again I can apply the conservation of energy principle, which says that the total energy E plus PE at the surface is nothing but E dash plus PE dash at infinite distance, which says that E is what? H nu, okay? PE is minus G capital mm by r. Why minus sign? The minus sign is because it is an attractive potential. Alright, so here I can write capital G, capital M, small m upon capital R is equal to E dash, which is H nu dash. So finally we have H nu dash is equal to H nu minus G capital M small m upon R, where small m is the mass of the photon because of its energy, which we obtained as H nu upon C square. Remember? E is equal to mc square, E is equal to H nu. So the mass of the photon is H nu upon C square. If I replace this here, then I end up getting H nu dash is equal to H nu minus Gm small h nu upon
Actually,
C square,
iodine will, in normal gravitational the close to sea level, iodine
is equal to nu
gonna sublimate.
1 minus
In a beaker on a hot plate, it will liquefy. It will be in its liquid phase.
So this is the change
Most elements
in the
carry some
frequency,
weird
or
stuff
rather,
like
this
that,
is a
but
new
for the
frequency.
up and down,
As a light photon
spin, strain,
completely escapes the
what is the
gravitational
energy
pull
value of
the
that
star
thing,
itself.
the
I can do a
measurement
little
of
bit
that
more
thing, the
calculation
time
here.
particle,
I can find
which
out the fractional
radiant
change in the
would
frequency.
cover some
The fractional
anti-numbers to
change
that.
between
Well,
nu
if that
minus nu
and
dash
the result had a
upon
little minus
nu
or a
itself, which
positive.
is nothing but del nu upon nu.
Plus,
So this
well,
is going to
no,
be
it's not hydrogen,
1 minus
100%.
nu dash
Well, some dark
upon
matter
nu.
in there,
So
and
the
the
fractional change del nu
anti-mu
upon
or
nu is
the
equal to 1
power,
minus nu dash
well, that's
upon
not
nu,
mu.
which is 1 minus nu dash upon nu
Anti-mu
is nothing
is
but
mu.
1 minus
Is it
1
tau,
plus
muon,
capital G
and electron?
m
Yeah,
upon
that's it.
C square R. 1 gets cancelled,
Somewhere around here, I don't know.
and the fractional change in the frequency of the light photon comes out to be G, capital M, by C square R. So this is the fractional change in the frequency of the light photon as it escapes the gravitational potential of the star completely. So this kind of a phenomena when light photon as it travels away from the star experiences a change in its frequency is known as gravitational redshift. Why redshift? Because if you're looking at the visible light, then the frequency of that visible light as the light comes out of the star's gravitational field will decrease, and a decrease in the frequency means that the light is going to shift towards the red end of the spectrum. So as the frequency decreases, the visible light will shift towards the red end of the spectrum. So that's why it's known as a redshift. And it is known as gravitational redshift because it is different from total redshift, where the redshift in Doppler effect happens due to motion between the source and the observer. But in this case, it is because of the photon spending energy to escape the gravitational potential of a particular star that its frequency decreases, and we see a particular shift in the frequency of the spectrum. So this is known as gravitational redshift, and this is actually a very important sort of a phenomena which is observed in our universe. However, I want to specify that all of these concepts are basically concepts coming.
I think we're into a little bit here. I guess that's the end of the clip. Yeah, okay then. Alright.